Okay, guys. I want to really share with you a bit of feedback based on the questionnaire I sent you last week, the Google form, and just really look at the areas perhaps people are most or least happy with. Um, There'll also be a little bit of a resource pack with this, so there'll be a worksheet you can look at, so just have your notes all in one place on this. But just really to start off with, I only had 6 replies, which from a class of 33 people is a little bit of a concern. So this may not be that representative, but fingers crossed it is. Well done to those people who did reply in time. But I just want to share really with you where you think you are in terms of the module 2 for the chemistry. So atmosphere, most people are fairly happy with that. Composition of the atmosphere, so 21% oxygen, 78% nitrogen, 0.04% carbon dioxide, and trace amounts of other things, noble gases and stuff. How the atmosphere is formed and changed over time. So volcanoes release carbon dioxide into the atmosphere, and water vapour. The water vapour condensed, that rained, it formed the seas. The carbon dioxide dissolved in the seas over time, started to form carbonate rocks, carbonic acid, and that locked away a lot of carbon there. Simple plant life started to form, so lots of algae, so then we got photosynthesis, that increased the amount of oxygen and reduced the amount of carbon dioxide. And a lot of those plants died and formed coal and oil over time, and that trapped a lot of carbon in the atmosphere. From the atmosphere in rocks. So you've got carbonate rocks, you've got carbonates in the shells of animals, but you've also got then the fossil fuels that then formed. Right, the word and symbol equation for photosynthesis. This one confused a lot of people, so I'm going to try and help here as best I can. So this is the carbon cycle, which you will have done and you will do again in biology, but carbon dioxide gets dragged out of the atmosphere by a process of photosynthesis. It's then put back by a process of respiration. Now, this is how I remember it. So, first things first, simple mnemonic. Oh God, we can't do everything. That is the equation for respiration. O is oxygen. G is glucose. The exclamation mark is where the arrow goes. We is water. Can't do is carbon dioxide. And this has no business being in a word equation, but it's plus energy because it's exothermic. It's how all living things make energy or generate energy from their food. And it's one of the important distinctions for whether things are alive or not. Do they respire? So learn that. That's respiration. Photosynthesis is the exact opposite of respiration. So there's my 2 learning things I've remembered. Oh God, we can't do everything. Photosynthesis is that backwards. So if I just reverse that, carbon dioxide plus water, arrow, glucose and oxygen, is just that backwards. Respiration is exothermic, so it stands to reason that the opposite would be endothermic, and it is. So photosynthesis is an endothermic reaction where it gets its energy from the sun. I've done it in green because it needs chlorophyll. So that's the word bit done. Now I've got to remember the symbol equation. So I remember this as the number of the beast. The number of the beast, if you read the Bible, is 666. If you remember those numbers, you can't go far wrong. Carbon dioxide I know is CO2. Water I know is H2O. Oxygen I know is O2. So I've just got 2 things to remember. Right, the first thing, 666. There's 6 of them all. And then glucose is a multiple of 6. C6H12O6. So that's how I remember that. 3 things. Oh God, we can't do everything. Photosynthesis is that backwards. 666, the equation of the beast. So hopefully that will help you remember that in future. If you can't remember it, write it out half a dozen times. It will stick in your head. Formation of coal and oil. Generally speaking, we're okay with that. Greenhouse gases, we're all spot on with that. The greenhouse effect and why it's important. So very simply, it would be too hot or too cold. The moon is right next door to us. It's ridiculously hot in the daytime. It's plus 100 degrees. Ridiculously cold at night time, about minus 200. Why? Because there's no nice atmosphere which sort of traps a lot of heat radiation, infrared from the sun, and maintains temperatures that are suitable for life. Greenhouse effect is a good thing. Increased greenhouse effect, global warming, that's a bad thing. Human activities, generally speaking, we're really good with that. Deforestation, burning fossil fuels, and methane produced from extensive farming with cows or with growing of paddy fields, rice. I can describe and explain the effects of climate change, generally really good. So, melting ice caps, rising sea levels, loss of habitat for various organisms, flooding, extreme weather events, droughts, all those sort of things. I can define carbon footprint. So generally, all right with that. It's a measure of the carbon produced, the carbon dioxide produced of a life of an event. So a certain event, what is the effect on the environment to do with that, and ways to reduce it and problems. So generally speaking, pretty good with that as well. I can list 4 air pollutants and the effects of those, a little bit weaker on that. Right, so worth bearing in mind, carbon dioxide is not a pollutant because it's a naturally occurring gas. The pollutant gases are the ones we chuck in the atmosphere, mainly from burning fossil fuels. So what do we get? We get carbon monoxide. It's toxic. It's really bad for you. Okay, blocks your blood's ability to carry oxygen around the body, so it kills you. That's one. You can have sulfur dioxide. There are sulfur impurities in fossil fuels, particularly coal and oil. So when you burn them, you produce sulfur dioxide. That gets into the clouds as acid rain, which is bad. It kills plants, it kills aquatic life, and you'll do that again in biology in the ecology module next year. You've also got nitrogen dioxide or oxides of nitrogen. They're produced in the engine. Internal combustion engines are hot, so nitrogen gets really hot, oxygen gets really hot. They shouldn't react normally, but they will. They will combine, and oxides of nitrogen get into the atmosphere. They make nitric acid. There's acid rain again. So there's 3 straight away. You could have had soot or particulates. That causes all sorts of respiratory problems, and I think we've got the bulk of them there. Okay, so oxides of nitrogen, oxides of sulfur, carbon monoxide, and soot or particulates. 4 pollutant gases and the problems they cause. Right, exothermic and endothermic with examples. Now we did this, and there's a video lesson on this which you can still access at this link actually. So if you go into my channel, you'll find it. It's worth watching if you can't remember. But you filled that in, and if you haven't done so, you should have done. Exothermic reactions give out heat energy. Okay, they release energy. So what's an exothermic reaction? Anything that gets hotter, so burning, combustion, acid and alkali reactions tend to be. So the temperature will rise, that's because heat or thermal energy is released to the surroundings. In an exothermic reaction, the reactants have more energy than the products. That means the energy change is negative, it goes down. An endothermic reaction absorbs energy, it takes in energy. So what's a good example of a reaction that takes in energy? We've just done it, photosynthesis. It's endothermic, it's taking in energy from the sun. It's trapping the sun's rays, turning it into food. So the temperature will fall. This is because heat is taken in from the surroundings. In an endothermic reaction, the reactants have less energy than the products. That means the energy change is positive. Okay, and I can draw energy profile diagrams for that. Again, a little bit hit and miss, but that's what they should look like. Exothermic reactants above products. Endothermic reactants below products. So make sure you've got your reactants in there, make sure you've got your energy change in there. So generally speaking, you were okay with that, or you're telling me you're okay with that. I can define activation energy and identify it on a graph, and this one surprised me actually because you were quite good at the questions when you submitted them. So what's the activation energy? Now we'll do this in module 4, we'll look at it in a bit more detail, but the activation energy is the minimum amount of energy particles must have when they collide in order to react. So particles must collide to react. This is what the spec says, I've just copied and pasted this. The minimum amount of energy that particles must have to react is called the activation energy. On a graph, it's a jump up here, and again there's a video on it. If you're not sure, do watch the video. But edited highlights of that video, think about Lego. If you get Lego, you've got reactants. Reactants need to be broken apart before they can be reformed as something else. If you're having to pull things apart, you've got to put energy in. Breaking bonds is a endothermic process. So you break the bonds in the reactants, you pull apart the Lego pieces, and they form the intermediate. There's a jump here. That jump is the activation energy. It's the energy required to break those bonds apart. If I'm smashing bits of Lego together, they've got to be hitting hard enough before I can break them. And then the products reform at the end down the bottom there, and that is that reaction there would be exothermic because the reactants are higher than the products. If it was the other way around, it would be endothermic. So that is what activation energy is. Minimum amount of energy required for particles to react, and it's a bump. It's a bump between the reactants and the products. I can explain the energy changes in bond breaking and bond making. We've just talked about that a little bit. So just going back up very briefly, I've got to put energy into break bonds. I get energy out when I make bonds. And if that is bigger than that, if the amount of energy that is given out making bonds is bigger than the amount of energy put in breaking bonds, then the reaction is exothermic overall. Okay. I can calculate energy changes in reactions. Now again, you were quite good at this and you're telling me you're quite good at this, so I'm not going to dwell on this too much. That's very good. I can describe how an electrochemical cell works. This is an area that you perhaps didn't feel so confident with. So very, very briefly, what is a cell? It's two different metals and an electrolyte, some sort of acidic solution or something like that. What you've got is a difference in the reactivity of the two things. One metal's more reactive than the other, and when they react, they're going to either gain or lose electrons. So one of the metals tries to lose electrons, and it's better at it than the other. Because of that, it forces its electrons onto the other metal. They can't go the shortcut way through the electrolyte, they have to go the long way. That's what a cell is. It's just two different metals with different reactivities and an electrolyte. That's all you need to worry about. Okay, the why of the reactions we'll look at in Module 7, but don't worry about it, really don't. I can explain the pros and cons of a hydrogen fuel cell. Easy peasy lemon squeezy. So those are they. Again, you can go back to the video lesson if you want. But the main one is nowhere near as polluting because it doesn't produce carbon dioxide. It does, however, produce water vapour, which is still a greenhouse gas. I can write the overall word equation for a hydrogen fuel cell, which you were really not confident with, but then you were more confident writing the half equations, which I would have expected the other way around. So, in a hydrogen fuel cell, the half equations, you've got hydrogen going in here. It reacts to lose electrons to form hydrogen ions. Those hydrogen ions migrate across, and then they react with oxygen, which is in the air, to produce water vapour. So, those are the two half equations. So, you've got hydrogen losing electrons and forming hydrogen ions. At the other electrode, you've got hydrogen reacting with oxygen to form water. So, those are the half equations, but the easy part of this is what's going in. Hydrogen's going in, oxygen's going in, hydrogen plus oxygen, arrow, water. The word equation's easy. Okay, so this is the symbol equation for that. If I can get that bit of sliding to disappear, go away. But 2H2 plus O2, arrow 2H2O. That's all it is. Just hydrogen plus oxygen makes water. That is the half equation, or those are the half equations. That's the overall equation. It's very, very straightforward. Hydrogen goes in, oxygen goes in because it's in the air, water comes out. Which is great if you're an astronaut, because what they can then do is either drink that water, or they can use solar energy on those massive solar panels that space stations tend to have, and that can then be used to reverse that reaction and split the water using electrolysis back into hydrogen and oxygen, so it can be regenerated. Okay, so that's everything. I will put the little resource sheet there as well, so you can just have a little bit of a look through stuff as a bit of a summary for the module. But hopefully that's helped a little bit. So take care of yourself, guys, and I'll see you all soon.